Ravi Kannan with us. Ravi was faculty here many years ago, and it's always great having him back. He then went off to Yale and then to Microsoft, where he's heads the algorithms group at Microsoft Research India. Ravi is well known for just work all across the area of algorithms, high-dimensional geometry, linear algebra algorithms, and just all across theoretical computer science. He's won a number of prizes, including the Fulkerson Award and the Knuth Prize. In particular, let me just mention, the Knuth Prize is given for kind of a body of work that's throughout a whole career. So it's a really big deal. And today he's going to be talking about work on topic modeling, combining algorithms, linear algebra, and high-dimensional geometry, all of his topics. So it's really great having Ravi.
Thanks, Alan. Thanks for the very nice intro. And well, it's always nice to be back. It's so nice to be back. I came here about 2 years ago, and I was hoping people forgot what I talked about. But I talked about topic modeling, but it's going to be different. Right? Even if you came to that talk, you'll find a bunch of new things. This is joint work with Srinji Bhattacharya, Harsha, Kushal, and Sutendra. Of these, Harsha was at CMU. We've a student of Tableau, and he was here a couple of years back. The talk is not just a regular, in a way, it's not a regular algorithms or theory talk. It will have that, I hope, but it's also sort of machine learning, which means a bit of the talk will be devoted to building the model and justifying it, and also some of the talk will give you some empirical results as well towards the end. So first, I'm going to introduce topic modeling. In words here, a lot of you know what it is, but in a picture in the next slide, which might be easier to follow. But basically, the idea is you have lots of documents, maybe in the millions, right? Each document you view as a vector of word frequency. So it's a bag of words model, so you ignore context and everything. Just write down how many times each word occurs over frequency, normalized to 1. Which is a standard thing to do. Now, you can do analysis of each document, figure out the most frequent words in the document, etc. What topic modeling tries to do is analyze the whole corpus and figure out correlations, right? Let's say that there are a certain number of unknown topics. Topics are not given to you. Topics are also just word frequencies, again, bag of words. So if the topic is sports, it'll have batsman or base, or those words more frequent and other words not. And you assume that you posit that each document is approximately a convex combination. We'll see why approximately. And the idea is the problem is given the corpus, find the topics, right? It's NP-hard in general, worst case. So we give it some help with a hidden hand or a stochastic model, right? The stochastic model which generates the data, we assume, that will make the problem easier, we hope. It's not worst case anymore, right? And the most famous model is latent-Dirichlet allocation by Blyman and Jordan. And again, I'll say it in words, and the pictures next slide, right? So it generates a distribution of topic weights for each document. So I'm going to generate a document. I say this document is going to have half politics, 1/3 something, 1/4 something, etc. I generate those weights first using a particular distribution, Dirichlet distribution. It's not important to know what it is, but that's what they hypothesize. And then you take a weighted combination of the topics of word probabilities for the document. So that's a compound topic, if you will, a weighted combination, and you generate words according to this. Nice theory in many applications, but the learning problem is very hard. It's NP-hard in general. A lot of even sub-problems are NP-hard. So here's a picture that explains topic modeling, hopefully completely. Okay. So what you're given is this term document matrix. So here are the words in your dictionary after some pruning, and here are the documents are columns, and I give you for each document what the frequency is. So 9% of the words are the word election there, 11% are Putin, and so on. These are not arranged necessarily in any order. I've arranged them so that you can see them nicely, but they are not arranged in any order. You're just given this matrix. H stands for high, and I'll explain that in a minute. So you see that the first document has a very high, not very high, but high frequency of backer and match, right? Now, what you're supposed to figure out as output is that this corpus is discussing 3 topics, and the topics are named also just by word frequencies. Topic 1 puts frequency 0.38, 28, and 27 on the first 3 words, and a little bit extra on both words, and so on. Topic 2 puts weight on these 2, topic 3 puts weight on these 2, right? Now, a human might stare at this picture after it's generated, after it is found, and say, okay, the first topic is politics, the second topic is sports maybe, or whatever, baseball maybe, I don't know. The third topic is weather. Well, I gave this talk in Seattle, so I said it's weather or Seattle. Just to indicate that the topic names are themselves not given. You have to get the next full factor of human interface. Now, document 1 is roughly a particular combination of topic 1, 2, and 3. They're all. The particular combination is 0.3, 0.4, 0.3. That's not exactly document 1. So document 1 has been generated perhaps by taking this combination, which amounts to this. And then the stochastic model tosses coins. So it generates the topic weight, generates this, and it picks words according to a multinomial with these probabilities. That's what you see. You see at the end the words generated. You don't see, of course, this, and you don't see that. This is one picture, but a real picture to remember. The geometry is very simple, and that's probably the picture to remember, the geometry of topic model. So in this case, there were 3 topics. They are the corners of this triangle. Because 3, it's a triangle. If it's K, it would be a K simplex. And these are exactly the topics we saw on the last slide. You don't have to remember them, but this corner puts high weight on those 3 words. The second corner puts high weight on those 2, and so on. You're not given the triangles. What the stochastic model has done is taken a convex combination of the corners, those are the crosses. The cross is the probability vector for one document. I don't give you the crosses. The crosses are all inside the triangle. They are convex combinations. It would be a lot easier. The problem would be nicer and easier if I gave you the crosses, because then you're just finding the convex hull of the crosses. What I give you is the circles. Circles are the observed documents, right? They are generated with these probability vectors, but the variance is enormous. And that's because I will only give you a small number of words from each document. If I give you infinitely many words from a document, then the crosses and circles will coincide, but I give you a very finite number of words. So the circles are pretty far, actually. Certainly some of them are outside the triangle. In fact, many will be outside the triangle. Okay? So given the circles, find the corners of the circle. That's a problem. Geometry.
So we assume some sparsity condition on how you combine things. Otherwise,
So,
you may not get
no.
anything close to the corners.
So I will have to assume that I get something close to the corner. So we do assume, we will make, I'll explicitly say what the model assumptions are. Indeed, it may be that all my convex combinations are the center point, and I only see points around the center, and I can never get the triangle. So I do need to see things around the corner. So things around the corners are documents purely on one topic.
Yeah, so sparse combination.
In fact, single, yeah. We assume single usually, and empirically that's supported. Again, I'll state the assumptions carefully. Okay, so LDA is a generative model, hand as the term topic generates. It's just a repeat of what I said. Except now I generate, once I have found the weighted combination of topics for a document, I generate M words in IID trials according to the weighted combination. Now, that's a generating model. The learning problem is I want to find, let's say, the maximum likelihood estimator of the topic matrix. That's, again, sorry. I give you the circles, and I want to find the maximum likelihood estimator of the corners. And that's hard. Even subproblems of this are hard. In fact, even figuring out the likelihood of a particular thing is hard. Now, so we have hidden variables, which are topic weights vector for each document. That's what I described already. Or even more detail, you can say that each word is generated according to a particular topic. So you take the topic weights and generate words, and each word is generated. And I want to find the topics for each word. By the way, some of these details are not important for you to remember, except that the triangle is nice for you to remember. So one traditional algorithm, in fact probably the most used algorithm for LDA, is run a Markov chain. So you associate, there are k topics, you associate a topic with each word in each document. S documents, m words each. So you have so many states in the Markov chain, and you run over these states. Markov chain. So for instance, this is the latest paper, the state of the art. They made a lot of improvements in each step to speed up the steps of the Markov chain, but proving mixing seems very, very tough. I mean, I think people have thought about it, but it's unclear that, it's probably not rapid mixing perhaps, or difficult to prove. But empirically, it's very successful. Okay. So, with no proofs, then the other traditional method is variational inference, where they have a topic matrix and they use a gradient descent kind of algorithm to modify the topic matrix. I will not describe these in detail, except to say a lot of empirical success, but we are lacking still proofs of convergence. Now, I will talk about, the talk is about having algorithms for which you can prove time bounds and error bounds. I'll come to that, but first I want to talk about scaling up. I want to scale up two things. I want to scale up the number of topics and the corpus size I can handle. Okay. So, but scaling the number of topics presents a conceptual problem, which we'll tackle first, and then we'll see how to scale up number of corpus size. That presents an algorithmic problem, which we'll also tackle. This is conceptual model problem, and that's algorithmic. So, the vocabulary size, let's say if it's English, it's 5K or 10K or whatever. It's not enormous. The corpus size can grow. So if you took, all news articles of a particular year, or if you took sort of many databases, they're pretty large, tens of millions, right? So we would like to fit a very small number, 5K topics alone to this many documents may not be the ideal thing. You would like to fit quite a lot more topics than 5K, than the vocabulary size. But known models conceptually or statistically make the number, have to assume the number of topics does not exceed the vocabulary size. The rough reason is the vocabulary size is sort of the dimension. The triangle wasn't the number of dimensions, which is vocabulary size. It was a triangle, of course, but it wasn't 5,000 dimensions. Okay? Therefore, that basically forces the number of topics to be not more than that. And that's a problem, because we want topics to grow much more than that. So we'll see why this, I will make the statement precise that this, you need that. So you have a data matrix, we want a topic matrix maximizing likelihood. So there's a little bit of statistic, but hopefully you can believe me. But the first one is simple. So if I'm allowed D topics, D is the vocabulary size, then I can just take the topic matrix to be the identity. This is very simple to check. And if I take the topic matrix to be the identity and the weight matrix to be A, that's a good fit. That's an MLE, in fact. That's a maximum likelihood estimate. It's very simple to see. Okay? If I allow you as many topics as words. But every topic is now a single word. Obviously, it's a trivial model. You don't want this model as the answer. Okay? So if you allow K to exceed D, you can get this answer if you're finding an MLE. And that's not very useful. So is this a problem with only K equals D? No, in fact, K can be smaller than that. D words, but there's a smaller number of words which form most of the frequency in general, empirically, right? That's this law. So MLE is still trivial if you have K greater than that small number of words. Each topic will still be a single word. This requires a proof. It's not very difficult. I won't give you the proof. This is a short argument to say that. Okay? So basically, you cannot allow the number of topics to grow, but we would like to. Problem 2 with growing K is the number of free parameters grows, right? Each topic gives you D free parameters, a lot of free parameters. That means the model overfits. And related to that is the problem that the sample complexity as well as running time grows a lot as the number of topics grow. Known through algorithms, it grows actually like a high polynomial. There have been attempts, of course, to treat this k greater than b problem. I put up two of these. This is a hierarchical model, and this is a model that's based on taking bigrams and trigrams. I'm not going to describe it in detail to you. So the problem was I couldn't go k above d, so why did I take bigrams? There are d squared bigrams. Maybe I can shoot up number of topics.
Like consecutive? You mean consecutive?
Yeah, bigrams means consecutive. In this paper, actually, they don't take consecutive. And you can also take in a narrow window. So that's another thing you can do. So in any case, it blows up the vocabulary size to the square of the vocabulary cube order. But it also blows up running time, it blows up sample complexity. So that's not something we would want to do. So here's how we solve this problem. We are going to introduce a new model. We call it deep topic. Well, we have to choose an objective there. It could have been something else, but we chose deep. What is it? So you will now only have a smaller number of basic topics, and each deep topic is just an ordered pair of basic topics. The intuition is very simple. The intuition is in a library you have a primary and secondary subject classification, right? So the list of subjects is the same for primary and secondary. One of them is primary, one of them is secondary, one of them is tertiary. But what we are going to do. So if you allow if you allow primary and secondary Qs 2, Q could be 3, 4. It doesn't make sense for Q to be very large. Basic topic is identified by a set of keywords. So the intuition here is topics are anyway identified by keywords. There's no way to name topics except by words. So each topic is identified by a set of keywords. And now if you have pairs of topics, you have pairs of sets of keywords. And we will show that the central problem we solve, it is enough to find the basic topics. So again, I won't describe it exactly, but it'll turn out that it's enough to find the basic topics, because you can find the basic topics, you can find the primary topic in a document, you can say what's the next high frequency set of keywords, that's the secondary topic, and so on. So we don't have to solve a k-size problem, we have to solve only a k-naught size problem. So the sample complexity and so on is not so bad. So basically the assumption is now the topic matrix factors into a product of 2. The number of free parameters is not very big. We also allow certain types of noise that are not allowed in other models. So this is the model for increasing the topic size, and hopefully it's clear. I mean, any questions? Yeah.
So what's the difference between having, say, a primary class topic A and secondary B versus being a mixture of, say, being 80% A and 20% B?
So, yeah, exactly. Good point. So what we are doing here is by saying, M2's columns tell you how to mix primary and secondary, right? We are allowing only some mixtures. We are not allowing arbitrary weighted mixtures. We are restricting the freedom you have to mix basic topics. And that makes our job easier. So it's a restriction, and it makes our job easier. In general, there's no free lunch. I have to pay for having very many topics. So I cannot have k degrees of freedom, right? I don't have that. I have only k naught plus this whatever number of degrees of freedom.
And so I guess it's counterintuitive, or it's not, yeah, so what's the intuitive explanation for why this conveys more information than just the vector of the basic topics?
Okay, so I'll give you a couple of examples. So I'll give you a couple of examples, but nothing is perfect because this is a model, right? So one example is if the branching so let's say the hierarchical topic model, which is a traditional thing. Let's say you're talking about all universities in Pittsburgh or something. First level you split into CMU, UPIT, whatever. Then you will have departments under it. But the names of departments and the names of whatever, faculty, students, those kinds of branches are the same across the whole tree. So the total vocabulary on which you're branching is is not going to vary, right? But I think, is your question, why am I restricting, or what am I gaining by?
Yeah, so, yes, it's not, right, it's not about like why you can do this, but what does this,
What does it buy you?
yeah, what does it buy you over just having the, like in the university example, just like the vector of like, math department and freeze would be enough. An unordered vector of those would be enough.
Just
to
freeze
tell you-
would be enough.
Yeah, just freeze would be enough, exactly. So what's, so how does the order, what are the examples where the order gives you more information? I guess sometimes I can imagine examples where you change the order and it means something different. Like-
Yeah, no, the order, it's just primary and secondary subjects, right? Why do we have primary and secondary subjects? Because it helps you, and in some cases it should. I mean, there's no proof, there's no.
No, sure, I understand.
Yeah?
So how does the generative model, so is there still like an LDA type probabilistic generative model associated with it, or is it?
Okay, so I'll come to that. We don't have a generative model.
Okay.
We don't have a prior.
Okay.
So that's one of the things. So we're generalizing generative models as well.
I see.
Yeah, so that's a good question. We don't have a generative model, we just have assumptions which generalize. Okay, so the second thing I want to scale up is corpus size. And here again, I'll give you first a bird's eye view and then state what happens. So one possibility, I have a very large corpus. I can't seem to work on all that. Let me draw a subsample and work on that, right? That would be first thought. I claim that's not a good idea. Why is that? Because so if you go now back to LDA, not our situation, but if you go back to LDA, LDA or anything posits a stochastic model in any case, and then I'm going to pick a random sample out of that. That doesn't make sense. I could have instead been given the smaller sample. I might as well assume that the stochastic model gives you as many samples as you need to learn. And so subsampling is not going to be a good idea. Then you lose, then you won't be able to learn, right? So you can't do that. Second thought, can you carry out most of our steps on a subsample? And the answer we show is yes. I'll give you the detailed answer as we go on, but first I want to give you a one slide bird's eye view of this. The idea is this. The final answer depends only on the pure documents. That's the question that Venkat asked. So that's things near the corner. The final answer is going to say, I'm going to identify the things near each corner and average them. Okay? Those are the pure documents, almost purely on one topic, corners of the triangle. So we will show that a document, how do you know when a document is pure? We'll show that it's pure if and only if it has a high frequency of what keywords, we call them catchwords. Okay? I'll define them in a minute.
Are you assuming that stop words have been removed?
Assuming?
Are you assuming that stop words have been removed?
Yeah, so I'm going to, I'm assuming the usual pruning, all the pruning is done, right? So otherwise they will be the catchwords will have to be exclusive for a topic. You'll see that stop words won't work, but yes. I have to define catchwords. Catchwords are things that identify a topic, basic topic. So we'll prove that pure documents are identified by high frequency of catchwords. And now, if I can subsample enough documents to find catchwords, then I'll be home. Then I can use the catchwords to find pure documents. So, here's the question. Does uniform random sampling work? Can I uniformly randomly sample some documents and hope to be able to do this? The answer is no, because it's got to involve some important sampling, because we need to stress documents that are catchword heavy. We have to do this before we know what the catchwords are. So that's the catch, but we will be able to do that. So, in fact, it turns out, and this is sort of a nice connection, so it turns out that a staple of randomized linear algebra where you sample columns of a matrix with probability proportional to the squared length of the column turns out to be the right thing here also. I'll have to describe this to you later, but it turns out that that can be used to get catchword heavy documents sampled more. So we will see how to do that. So the moral of this story is, while the corpus is very big, and we do need it to identify pure documents. There aren't too many pure documents. If I subsample, I'll be in trouble. So we need the whole corpus, but we can do most of our work on a sample of the corpus, provided we do important sampling.
I didn't get something. Did you say what a catchword was?
I didn't say. I'm
Oh,
sorry.
okay.
I will say. Yeah, it's upside down, but I'll say what a catchword. Catchword is just like a keyword for a topic, but it's more exclusive to the topic than other topics, and I will define it.
That helps.
Yeah. Okay, so yeah, I changed some of the orders. Okay, so then I put up this general philosophical slide just so that the whole talk is not controversial. It's not very interesting. So this is sort of well, I mean, it's fairly dramatic, but it's ML and theory, right? So the nice things about ML and statistics, there's a lot of focus on the model, and usually there's very nice statistical mathematical underpinnings. And then once the model is home, is there, one uses perhaps simple algorithms. Lloyd's, I don't know, k-means or expectation minimization, gift sampling. These are some of the names I put up. I won't explain all of them, but you're familiar with many of them. And also, you generally have very simple proofs of convergence to a local man, of course, right? It would be bad if even that didn't happen. But often proofs, finite sample proofs, not in the limit, finite sample proofs and time-bound closeness to global optima are difficult to come by or not there. What theory would like to do is do these proofs, okay? And here I need the following. We would like to prove, so in unsupervised learning, as in many problems of unsupervised learning, you can't prove that you got the right answer because you don't know the right answer, what the right answer is, right? But let's pretend that we had a generative model. I promise you that there was a generative model. Then can you, in polynomial time, approximately find the generating model from the data? Okay? And approximately means there are some errors here which have to be bounded. And you want to be able to do that. In theory, perhaps sometimes we use very complicated algorithms, but it would be nice to do that with simpler or widely used or usable algorithms. So I put up some of the many efforts in theory. This is not a complete selection, but certainly for Gaussian mixture models, for instance, we do know a sequence of papers in theory which prove this sort of thing. Lloyd's algorithm, there's a paper we have, and then there's a paper of two students from here. I guess Orr is the first name, but check that now. So, who are algorithm students. And alternating minimization for matrix problems, there's been a lot of attention now. So these are some of my colleagues from Microsoft India. So there are a bunch of such proofs, but perhaps it'd be nice to do more on these proofs. That we can find simple algorithms with proofs and pay attention to the model. That's what I hope we'll do. I'm going to abbreviate provable, polynomial time and error bounds by provable. This is not to say that things that don't have those, or proof blind or anything. It's just this is what I mean by provable. Only the specific thing, right? Okay, so now I'm going to describe to you more, in a way, quote unquote, more general problem than topic modeling. Topic modeling is in this genre that you're given an input matrix. This was your documents, the input documents, right, in that example. It could be other things. Non-negative matrix factorization is more widely used than topic modeling, perhaps, or used differently than topic modeling, so it comes up in all of other contexts. You have a non-negative matrix, you want to factor it into a product of two non-negative matrices, but I give you the width of this, right? That I give you that. Unlike, so if I don't have non-negativity, then this is, if I don't have non-negativity, this is singular value decomposition, this is linear. With non-negativity, it makes it NP hard, unless you assume that the width here is constant and we know some algorithms. This is exact NMF. A equals BC. The real problem we want to solve is approximate non-negative matrix factor, where this is not an equation, it's an inequality. And typically there's enormous amount of noise. If you put topic modeling in this framework, the noise is really sparse data. So you have to worry about the noise as well. So you can normalize all the columns to sum to 1. That's just a simple observation, and I'll use that observation in a minute. So here's a picture of, before I give you a picture, I just want to give you just a list of algorithms. So this, in a way, the approval stuff started from NMF and then went to topic modeling, and there was a bunch of papers, some of which I'll refer to as I go along, but I want to give you a picture here, the same picture as we had, right? Except now, this is also the picture of non-negative matrix factorization, right? So now there's noise, so the real, if A equals BC, you get the crosses, right? And you want to factor it into the corners times weights. If A is approximately BC, you're given the circles, just like in topic modeling, and you've got to factor them. Okay. Now, here's a simple observation that probable algorithms started with in some sense. Suppose there was one circle at every corner, exactly sitting at the corner, right? One circle at every corner. And assume that no circles are way outside, then it's just finding the convex hull. You can do it by linear programming. Okay. But you need many linear programs. It was costly. It was improved. In one of the papers I put up last slide, it was improved to just one convex program. Still, the convex programs are nice, but perhaps they don't scale up to the levels that we want to scale up. And also, this was not robust to noise. So all those problems are there. How are we going to solve them? We are going to solve them by making assumptions, and now I come to the assumptions and define what catchwords are now. Okay. So here are the main assumptions. So there are two slides of assumptions. So first, each topic has a set of what are called catchwords. What are catchwords? So each basic topic. This is the smaller number of topics, right? Not the complex, basic topic. So each catchword has to have a higher frequency in the basic topic than other topics, strictly higher, by a factor of 1.1 or whatever. And all catchwords for the topic together have decent frequency. So we assume these two. Now, these assumptions, you can question them, and I'll come back to that. But it contrasts with earlier assumptions people were using called anchor words. And I won't define anchor words except to say what the difference is. So the anchor word assumption would have assumed something like a particular single word, it's not really a single word, but anyway, so a particular word occurs only in the topic baseball. So it's exclusive to a topic. Anchor words are exclusive. Okay? And now, furthermore, high frequency. Every 10th word is only. In contrast, catchwords assume not one word, but several words, collection of words, and their frequency is not exclusive to baseball, 1.1 times the frequency in other topics. And also, one word is not high frequency, a combination of words. So it's more realistic, and in fact, I'll come back to that. It's empirically verified. For those of you familiar with latent Dirichlet allocation, if you assume a Dirichlet prior on the topic matrix, then these are provable. So I'll mention that later. So the second assumption is that each document has a dominant topic. One topic which high weight, the primary topic of the document. High weight does not mean 0.9, it means 0.2, let's say, whereas the average would have been 0.01, there are 100 topics. 1 over 100 instead is 0.2. And furthermore, the weight of non-dominant topics is strictly less by a definite amount. And then there are these things near the corners. So we assume that each basic topic there are a number, a small fraction of pure documents whose weight is very high, 0.9. So these are documents almost exclusively one basic topic. Again, that seems questionable, but it's empirically verified, and it's true for Dirichlet, right? Dirichlet distribution tends to put very heavy weight on the corners of the simplex. So this is true for the Dirichlet distribution. So all three assumptions are empirically verified, also provable. Yeah?
So I guess this assumption means that in your pairing, this secondary classification can't really associate mostly with a fixed primary classification, right?
It will not associate in general with the fixed primary classification.
I mean, this prevents
But
that.
we are restricting the pairings by this other matrix so that not all pairings can occur. also independent. Okay, so now a bit of a story about our algorithm. Before I start, our algorithm involves singular value decomposition very crucially. So here is a slide called SVD gets a bad rap. Predating topic modeling, there was late semantic indexing by Suduma and others. They proposed SVD as a denoiser. And then Crystal, probably Mithri and others showed that LSI probing does topic modeling, but they had to assume for their proof, not necessarily necessary always, but for their proof they had to assume that each document is purely on one topic. So, unfortunately, they proved that, which is good, but people assume that that implied that SVD cannot help when there are multiple topics. It's not true, but there was enough attempts to do SVD, and it didn't seem to work. So people thought that maybe SVD will not do the job unless you assume something drastic like this. So in fact, even in theory, people wrote papers whose title was Beyond SVD, and so on and so forth. I mean, sort of saying SVD won't work, here's something I can do that will work, right? But then these people came up with an SVD-based algorithm of topic modeling. It was not efficient, but still it was based on SVD. The thing with SVD is, okay, so one question is whether it can work. The other question is time complexity. Well, we have a lot of improvements because of numerical analysis, but still it's difficult to work. So the problem sizes we are thinking of was number of topics, 10,000 plus. This is number of non-zeros in the billions, number of non-zeros in the matrix, right? In the billions, we do solve problems of that size. Now, for that, SVD is difficult to scale up, right? So one new insight is that subsampling, that I mentioned already, subsampling the matrix and doing SVD only on the subsample works, right? So that's the insight. Now,
So you use SVD to find the topics, or?
So yes, indeed. So we find actually the dominant topic, dominant basic topic for each document by clustering. So quite a bit of the work is done by clustering. But still remains the rest of the stuff. In fact, maybe I'll have pictures very soon of what the algorithm, how the algorithm is going to find things. So here's the algorithm. The main steps and the various pictures. So first thing is thresholding the data, and I'll tell you why that's important. Then we do SVD and cluster by dominant topic. So this step finds the dominant topic for each document, dominant basic topic for each document. And that is used to find catchwords for each basic topic. And catchwords are just going to be the most frequent words in each cluster, just raw frequencies. That's used to find pure documents, which are the documents with the highest frequency of catchwords among all documents. Right? So find catchwords, find pure documents. So why do we do all, this is called threshold SVD. Why do we do threshold SVD? Here are some selling points for it. Provable bounds on the reconstruction error in time. We'll sort of show that quality metrics is better. It's highly parallelizable, which we haven't done yet. And it scales up. Okay, good. So now a picture description of some of the steps. So thresholding. So this picture I've rearranged. This is not the way the data is given. I've rearranged documents so that documents with dominant topic 1 come first, 2, 3, 4, and so on. So they are arranged, columns are arranged topic-wise, dominant topic-wise. Rows are arranged with catchwords for topic 1 first, 2, 3, and so on. And the black stuff is non-catchwords. They are not catchwords for any topic. And this is typical. Quite a bit of the frequency is occupied by things that are not necessarily distinguishing between topics. Okay. So the ideal picture would have been very thick blocks on the diagonal and almost nothing outside. You see that the picture is sort of looks like that. This is after finding catchwords. I don't know this picture per se, right? So picture sort of looks like that, but not quite. But thresholding just says for every word, for every row, I find a threshold and roughly zero out everything below the threshold and make everybody above the threshold 1. That makes the picture much nicer. this is to be all proved, and I'm not giving you the proof, but we can prove that it makes the picture much nicer. So thresholds are row dependent or word dependent. So for each word, there's a cutoff frequency.
Ravi,
Yeah.
is this synthetic data or actual data?
This is actually it.
And so is it, do you know, if it's actual data, is there a well-defined ground truth, or could there be like two totally different solutions that would
No,
give
there
different?
could be two totally different pictures which are right, yeah. There isn't a well-defined ground truth, unfortunately. Yeah, it's problem all this, right? We don't know ground truth. It's actually an interesting question whether you can find K even by the algorithm itself, right? That's a long-standing question. Okay, this might be a picture I took from Melbourne, actually. This picture. Okay, so then we do cluster. So we do threshold and then we cluster. We use k-means clustering to the data after thresholding to get dominant topics. But of course, you know that k-means clustering does not have a proof of convergence. So this is the paper. Also, I should have put up Aveshti and Sheffield here. The point is, what is the point? The point is, if you have 3 clusters here, if I start with the 3 cluster centers, 1 each cluster, I'm home. If I unfortunately start with 2 cluster centers, 1 cluster, I'm dead. You can convince yourself that k-means will never recover. What we prove is that this is the older result. What we prove is that after thresholding and doing SVD, you will get a good set of starting clusters. So the seed centers are better. So you don't get into this problem. Okay, so another picture. Now this is an overview. We'll stare at this for a bit because it's an overview of the algorithm in some sense. So what have I done so far? Again, I have the circles and crosses. Crosses I don't know, circles I knew. And I've clustered by dominant topic. What does that mean? That means I've drawn these 3 red lines. So all I've done so far is drawn these 3 red lines and said, all of these documents have dominant topic mu1, these are mu3, and these are mu2. Right? That's what I've been able to find so far. Now, if you had a normal clustering problem, you would just take the cluster centers and you're done, right? You found the clustering, you take the center of each cluster and return that output. But now I'm not going to be happy with that, right? I want the corners, so I really want the outliers. So I've got to find the corners rather than just cluster centers. So how do I do it? So this, maybe I'll run over fast the next couple of slides. So I'm going to use the clustering to find catchwords now. So catchwords turn out to be, so you could do a bunch of things. You could say they're the most frequent words in some sense. It turns out this is the correct sense, the fractals, because for them you can prove things. So we proved that words with the top fractile in this cluster, which are greater than 1.1 times other clusters, these form the catchwords. And pure documents are also found by a fractile, and it's a different fractile, which is the fractile, the top fractile documents which have a high frequency, high total frequency of the catchwords. They were roughly near the corners. So in the picture, we didn't have catchwords, it's only the document space that was shown, but the catchwords help you identify near the corners. And then once you found pure things, it's very simple. Okay. Now, I will not have time to go over how to find the deep topic from the basic topics, but let me say one word about it. So once we have found catchwords and catchword frequencies, then we compute the most frequent set of catchwords is the primary topic, the second most is the secondary topic. Right? So it's pretty simple. That gives you the weights also. For those familiar with topic modeling, we don't have to solve the inference problem. So it's a hard problem to find out topic weights for each document. We don't have to do that because we get catchword frequencies. That's a good proxy for the inference problem, it turns out. Okay, so far I present results on 3 data sets, and I'll only compare to light LDA, which is the state-of-the-art algorithm that I gave you. There are other algorithms that don't necessarily scale to this level, right? So there are The first two are open data sets, this apparently not, right? So let's see, this here means 2 billion tokens. A token is a word in a document, right? So Wikipedia database has a total of 2 billion tokens. The number of non-zeros, because some words occur multiple times, is fewer than that. This is the vocabulary size. The number of documents is 11 million or so. Okay, so again, I don't have too many tables. I have a couple of tables. STP is our algorithm. Actually, I forgot the expansion of STP, but it's our algorithm, right? And this is light LDA. The 10% means that we subsample, and here we did not subsample. So running time, you can see, is better. Although I should say, in the case of light LDA, they run the Markov chain with clip sampling for 100 iterations, right? That's what we're comparing to, because that's the number of iterations they took. So this 10% means 10% sampling. Now, topic coherence. So this is the first quality measure. So I should step back and say, there is no one satisfactory measure. There are several measures, and there are certainly discussions about what's the pluses and minuses of each. I won't go into the details, but let me just say that take this in a sense with a pinch of salt. These aren't absolute measures. Right? Topic coherence is the log of the correlation among the top 5 words of each document. So higher it is, it's better. It's a log of the probability, so it's negative. The higher it is, better. This is just showing that sampling doesn't lose as much, up to about 2,000 basic topics is what we've done here. This is just our algorithm, sampled and unsampled. Okay. Now this is comparison with, I think I have a couple of slides comparing to like LDA. In topic coherence, generally we do better except on the 100K. Boldface is better, right? So let's see, let's go over one number. 10K topics, 10,000 topics. These are compound topics for us, and just topics for light LDA. We get minus 30.40 as topic coherence. Light LDA gets minus 44.47. Again, the higher the better, so correlation. On the other hand, in log likelihood, light LDA is better here as well as there. That goes with explanation that I should give. Light LDA, first of all, light LDA is computed by individual algorithms because there are, LL is log likelihood. LL is NP hard to compute, and therefore you compute it only approximately. Let's see, for us, there's an extra complication because we compute it using standard algorithm mallet technique, so effectively use it. But the usual computation assumes a Dirichlet prior. There's no prior for us, so these numbers you have to take that qualification. And scaling of corpus size, I didn't tell you very much, and one slide on that before we finish. Want higher probabilities. So, turns out, maybe I should make this one. We use the whole corpus only twice. First to figure out the sampling probabilities, and then to get the pure documents and everything. So a bulk of the algorithm, except for these two, uses only a sample. And this is a reconstruction error on a small number of topics. Now, what is a reconstruction error? So this is done on a semi-synthetic data set. So you take a semi-synthetic because you take a real data set, you fit an LDA model, and then now you know the ground truth. You pretend that the LDA is the model you got is the ground truth, and then you generate according to that. And then see if you recover what you generated from. You take the L1 error of that, and that's better for us, better for our algorithm than like LDA. And of course, the big point that we do is prove that reconstruction error is small, right? So it's nice that we do that. Okay, that's it. Thank you.
Are there any questions?
Oh, yeah.
Sorry.
I was a little confused by one thing, that early you said sampling doesn't help, and then afterwards, in the rest of the
Yeah.
talk, sampling helps all the time.
Yeah, sorry. What I meant to say was, it is a stochastic model. Anyway, we are given samples from a distribution. So just subsampling that doesn't help, because that's just like. as
But
a
then you
feature.
are sampling.
Yeah, as a feature of it. But we do some computation, and so this last slide I should emphasize that.
After the
So we do
computation.
some computation to figure out the probabilities with which we want to sample, which are not uniform. So then it helps.
Thank you.
Yeah.
I'm especially, I guess, a little surprised at the last results because I mean, light LDA, I mean, you'd think that light LDA, that, I mean, it's built on the LDA assumption that you figured it would do better with respect to reconstruction here, but yours actually does better.
Yeah,
Is
so-
like, do you have like an intuition as to why that happened?
No, I don't have a perfect intuition, but let me say, so if you had used a variation method, because you're going along the gradient, it may tend to emphasize sort of outliers. This is not variation, this is knockout chain. But perhaps it's indicating you're not converged to the steady state, or identifiability is not clear. So it's all, those are all possible.
Yeah, do your resulting topics end up being coherent to a human? And, I mean, I'm having trouble reconciling the idea that all detailed topics are just recombinations of basic topics.
Right.
There wouldn't be more than one inside a basic topic.
So let me address that. So we did stare at a few of them a little bit. I can't promise that, we stared at the 10,000 topics enough to say that it makes sense.
Sure.
They seem to make sense.
Okay.
But that's subjective, so one would have to look at them. Yeah, so I think it requires further work to assert that this way of doing deep topic is precisely relevant to, a whole lot of, I mean, it's the first definition, so one has to examine it. It's not, I mean, it looks okay, it looks good so far, but in practice, exactly what happens, I don't promise, right? I don't know yet.
I'm a little bit confused why for NMF the region was shown as a context instead of like a conic region, because you're talking like.
I normalize the columns to like
Oh.
one, and I can do that anyway. I can normalize the columns of A, B, and C all. Well, if there's noise, I have trouble. In the exact case, I can normalize all of them. I can assume without all the generality that columns of A, B, and C all sum to one each. Then it's convex.
So one kind of natural question in this area might be, given a corpus of documents, what's sort of the fewest topics I need to explain the corpus? Do you have any thoughts on how you might convert that into a formal,
Yeah, that's a
criteria?
good question. Here are some quote-unquote vague thoughts, but I don't mean. So one is the non-negative ranks of the matrix. So basically, the non-negative rank of the matrix, at least under assumption, should be the right number of topics. It's probably equal to the rank under these strong assumptions also. Right? So one would like to say rank is the right rank.
Exact rank? Or?
No, so it's a numerical rank. So you will have errors because the probability matrix will be low rank, will be the correct rank. But A will have errors. The spectral anomaly error is bounded because the disturbance is a random matrix, and so it has good spectral behavior. So that rank, maybe, but I don't have proof. Yeah.
I was just wondering, when you were doing the clustering, what either like distance metric or coordinate system were you using in order to like place the words of the topics in the space?
So I'm using the coordinate system in which I'm given the data, no transformations.
Okay.
So for each word, we do some computations, and the clustering is done exactly in that space.
Okay.
But, okay, so, no, I see your question, so I should, okay. So in the thresholding, and I didn't mention this, in the thresholding, when a frequency of a word in a document is above a threshold, I don't set it to 1. I set it to something which depends on the total frequency of the word. So coordinates are biases, coordinates are weights.
Okay.
the thresholding process weights coordinates differently. So it's weighted to the square root of the threshold, and that's the correct weighting. Okay, so maybe that addresses your question. So
Yeah.
it's not the original space. The coordinates are weighted now.
Okay.
So I guess another way of doing this kind of hierarchical classification, which I think is different from what you did, if I understood it, is you could first have build your topics from the words, and these could be your secondary topics, and then you could build your primary topics as vectors of the secondary topics. This would give you something.
Oh, so you mean bottom up?
Yeah.
Okay, but the difficulty, okay, so that's possible, but the difficulty is this, right? The primary topics are distinguished by words that are important for them.
Yeah, that would not be the case.
Whereas if
here,
you came from the bottom, you may not see the difference. The learning problem would be hard, potentially.
All right, if there are no more questions, thank you.
It's okay, I think you could be. It's probably better.